So let's get started with this lab. If you remember, what we did here is we plotted a graph of absorbance versus the concentration of stock solutions. We took a zero point 0.4 molar solution, okay, and you did serial dilutions, and what you did was you diluted it in half to 0.2, and then you cut that in half to 0.1, and you cut that to 0.05. And so we had approximately 4 different known solutions that we calibrated our spectrophotometer with. So what we did is, notice at 0.4, okay, we measured a certain absorbance, okay? So the spectrophotometer was connected to the computer, and essentially we collected or measured the absorbance, which is the negative log of the transmittance, and that absorbance is due to the fact that the higher concentration had more particles of matter in it, absorbing certain wavelength of light. In any case, we entered the value. So we did this for these 4 points, okay? And we noticed there is a linear relationship. And what we did was we hit the regression button, which told us, or basically made a best fit line between the points. Notice this is not connecting the dots, it's a best fit line. And the reason why we do that is because, very simply, errors in either our dilutions, okay, or in the equipment themselves is going to lead to some variability, but there is a linear relationship. You know, A, or the absorbance, is proportionate to the concentration. If you have higher molarity, more moles per liter, you're going to have more of that compound if it has a color that's going to absorb more of the light. So that's why the 0.4 is highest, and of course it goes down. Now, what do we know? Well, at this point, with this calibration curve, what we've done is we've basically got our curve ready. Now, if you look at your data here, and it's hard to see, but the computer gave you your slope. We know that y is equal to mx plus b. And let me explain. This linear relationship between the known molarities that we calibrated our spectrophotometer with, this is called a Beer's law graph. Okay, Beer's law states that, very simply, absorbance and concentration are a linear relationship. So, knowing that, when we have this value of y, by the way, y is your absorbance, so I can get rid of this y, and so absorbance is equal to the slope times the x. The x, of course, is our concentration. So what we're going to do is, this relationship and these numbers that I have are going to allow me to be able to solve for the x, or the concentration, as long as I can measure the absorbance on this machine that was calibrated. So we understand all of that. Let's put the numbers in. Absorbance is equal to the slope, okay? Now the slope was given to me by the computer to be 8.979. So let's get rid of all of this and just make it nicey nice. And we have 8.979. 8.979. Okay, this is my y, this is my slope. The x is going to be concentration. I'll just put that as C. And plus the y-intercept, which will be negative because it's going to go through the negative line here, and I get a negative 0.26. Negative 0.2661. Okay, so I've got my equation. So if the computer can read me an absorbance, all I have to do is solve for C. So what you did in lab is you took your 4 or 5s, I think some periods did 5, took your 5 or 4 solutions, we entered them into the graph, and now we have this Beer's law graph, and we're going to use this graph, just like our homework, to answer a question about the absorbance of the unknown. If you remember, you guys massed out brass shot, okay, little BBs on a plastic weighing boat, and you massed it out. Maybe the mass was 1.47 grams. I'm just making that number up. And then what we did was we figured out how much nitric acid was needed to dissolve it. So generally speaking, I poured nitric acid. Okay, just that's me pouring, I guess looks like blood, but nitric acid into this. And of course, you saw that reddish brown gas leaving. That's the NO2. And after a period of time, all of our solid CO0 became copper plus 2, along with the zinc plus 2. Now the zinc plus 2, for reasons we've explained, is colorless, so we're able to actually measure the concentration, the molarity of the copper plus 2, because in crystal field splitting, it absorbs some wavelengths of light, which means it perceives to have a color. Okay, so knowing my grams of my brass, all right, knowing the grams of my brass, and knowing that I completely have oxidized my copper into copper plus 2, because the nitric ion, the NO3 minus 1, pulled electrons from the copper, and then it became NO2. Essentially, all of the copper that was in this alloy has now become these ions. So I have a beaker of ions. Copper plus 2 and zinc plus 2. Now, what we did was we poured that solution of ions and probably extra acid, and we poured it into a 100 milliliter volumetric flask. It's like a pumpkin with a label, but hey, there's a line. So we poured this stuff in here, okay, and it was very dark green here. And then once we made sure all the ions and liquid was in here, then we poured H2O in here, and then we diluted and added water, and we diluted this to the 100 milliliter mark. Now, why'd we do all that? Well, that will give me 100.0 milliliters of solution. That's my volume. Okay. What are we looking to find here? I'm trying to find the percent by mass of copper and brass. So if all the copper, party people, is what makes the color, then I can solve for the concentration of that copper with my calibrated curve. And how do I do that? Okay, well, we took this sample that was 100 milliliters and we poured some into a cuvette, an unsuspecting cuvette. I can't draw a cuvette right now, but hey, you get the point. So there it is. So we poured some into a cuvette, and then we put it through the spectrometer again. Now, we didn't add it to this curve. This curve is needed to solve for the C. So we actually measured in the lower left corner what the absorbance was. And let's pretend that I'm a princess, and the absorbance was, let's say, 1.63. I'm just making numbers up. 1.63. That's the absorbance. So you just put it in the spectrophotometer and just read that. And so the absorbance, and this would be in your data table, of my solution was 1.63. And the grams of my solution, okay, this is important, is here. This is an important value here. Now, by the computer reading that absorbance of the cuvette filled with the ions that were oxidized from the nitric acid, now we can solve for C. Now, how would we do that? Again, let's rewrite this and make this very neat. Okay, from the linear equation, from calibrating, A absorbance is equal to 8.979 concentration minus 0.2661. So we know the absorbance. We just measured the absorbance of the ions that came from the brass material to be 1.63. So now I'm just going to do algebra to solve for C. Using what? This is the linear equation that was developed by calibrating the curve. So to solve for C using our algebra, okay, all we're going to do is add 0.2661. That gets rid of that. And add 0.2661. We put that in our calculators. So 1.63 plus 0.2661. And that gives me, and this is just made up numbers, but you can follow along, 1.8961 equals 8.979 C. To solve for my C, all I'm going to do is divide by that number. Just doing some algebra here. Okay, so 1.8961 divide by 8.979 is going to give me my concentration or my molarity. And so let's do that. Divide by 8.979, and I get my molarity to be 0.211. And I could probably use 3 significant figures, and that is equal to the concentration of my copper plus 2 ions. That's my molarity. How is that helpful? Well, wait a minute. Okay, what are we after? We're after the what? We're after how many grams of really copper are in this sample to get a percent by mass. So knowing the molarity, and don't we know the volume? Party people. Molarity is equal to moles over liter. We should have used this equation once or twice. So we know the molarity is 0.211 moles per liter. And we know what? We know the volume is equal to what? 0.10 liter. Look at that. I want you to look at that, okay? So this times 0.1, if you have to do the math, you can see that we get approximately 0.0211 moles of what? Copper, because it was copper who made the light blue color. And now let's convert our 0.0211 moles of copper to grams. Hopefully this works out because I made numbers up. And there's approximately 64 grams per 1 mole. And I know I set this up wrong because I have the mole here. Always good to use your units. Okay, so you don't make the mistakes that I do. For every 1 mole, there's 64 grams. So, times this by 64. And I get 1.35 grams of copper that's in that brass object. Okay. Now, I gave you 1.47, so 1.47 is the what? Copper and the zinc. Remember, zinc is the other element that's alloyed with. Subtract 1.35. I think we can handle this without a calculator, right? And what we have is 0.12 grams of zinc. That's what the grams of zinc, but we really need to do that. The bottom line is 1.47 is the total. The part is 1.35 in my math times 100, and that's going to give me the percent by mass of copper in this brass. So 1.35 divided by 1.47 and times 100, and in this case, I get a 91.8% by mass. Now, you should not get something that high. All right, you should get something, well, I won't say what you should have because I want to see Monday what you have, because I have the exact percent that copper was made up of. So please look at the requirements of how to do this informal write-up. It's mostly the math, but I certainly want to do it more clear and neater than I did, okay, and more organized. But you should be able to understand that we were able to do analysis of the alloy, of one of the compounds of the alloy, by using the idea of crystal field splitting and color, and of course a spectrophotometer that takes into account the idea that a more concentrated, okay, compound that has a colored solution, all right, is going to have more absorbance than one that's lighter. Hope that helped.